Hi everyone, this is the third part of chapter 4. We're going to talk about the method of least squares, and we're going to start the conversation for calibration curves. Let's get started. Alright, so the method of least squares actually tries to find the best straight line through your data points. We're going to be applying this procedure in lab as well as in all the problems that we do here in lecture. As most of you already know, the equation of a straight line is y equals mx plus b, where m is your slope and of course b is your y-intercept. And the slope is defined as rise over run, so the change in y over the change in x. More specifically, the method of least squares finds the best line by adjusting that line to minimize the vertical deviations between the points and the line. Why only the vertical deviations? Well, usually there's more error in your y-axis than there is in your x-axis, and also it's a lot simpler mathematically to do the calculations for the vertical deviations than for the horizontal deviations, so consider yourself lucky. The line that gets generated minimizes the sum of the squares of the residuals for all the points. Those vertical deviations, by the way, are called residuals. Now let's talk about how they actually compute that vertical deviation. So why is it called least squares? Well, you have some deviations that are positive and some deviations that are negative. So to minimize the magnitude of those deviations, no matter the sign, we actually square them to create positive numbers. How do you compute vertical deviations? Well, you take yi minus y, where yi is where the actual point is vertically, minus y, where y is what the point is on the line. So basically you're just taking the difference of the point from the line. And to do that, you would take the actual point and substitute what y equals. Y equals mx plus b, because that's the equation of a line. So you just go ahead and substitute that in for y. So you have yi, which is the point, vertical position of the point, minus what y equals, mx plus b. And you square that. So that's what you see down here. It's yi minus mx minus b squared. So in essence, you're taking all the numbers and all the vertical deviations and you're squaring them, so you're getting all of these numbers in positive, which is what you want to do. That's why it's called the method of least squares. That Gaussian curve that's drawn over the point 3, 3 is just a schematic indication of the distribution of measured y values about the straight line. Obviously, the most probable value of y falls on the line, but there's a finite probability that that y value may be that distance away from the line. So that curve just shows you the probability of where you would be able to find the point about the line. Let's move on. Whenever you use this procedure of method of least squares, you're trying to minimize the sum of the squares of the vertical deviations. Whenever you do that, the slope and the intercept is fitted to the number of points. And it happens to end up being this equation that you see down here. Now this is a lot of letters, but really it's not that bad. All it's telling you is that you take the sum for the slope, you take the sum of all of the x's and all of the y's, and you multiply them together, times however many points you have, minus the sum of all the x points times the sum of all the y points. And then the same, obviously it's the same definitions for the variables in the bottom. And you have the equation for the intercept, which you see it's only using x and y and the sum of. So what we're going to do is create a table of all of these things so you have them, and you'll see that this is very simple. All you're doing is plugging in numbers. It's not rocket science. So I'm showing you the equations, and we're actually going to use these equations to calculate least squares for the points that I showed you previously in that graph. So let's go ahead and make a table with the 4 points that we have on the graph. You see that all we're doing here is getting all the x's, all the y's, and then multiplying both numbers and then squaring all of the x's, because we're going to use those in that equation that I just showed you. So if you notice, the first x is 1, the second x is all the way at 3, third one is 4, and the fourth one is at 6. So that's all we're doing. And we're taking the sum of it. And you see that the sum 6 plus 4 plus 3 plus 1 is 14. We do the same thing for the y's, and then we multiply both those numbers for the third column. So 2 times 1 is 2, 3 times 3 is 9, 4 times 4 is 16, so on and so forth. And then we square all of the x's, and that's how we get the numbers that you see in the table, and that's how we get the summations in the bottom. We just add all of those numbers up. Very simple. Let's move on. Now we're ready to compute the slope and the intercept. These are the original equations I showed you, and all we're doing is going to plug in the numbers that we already have calculated. So the number of points is 4. So that's why they have 4 at the beginning. Now you take the sum of x and y, which you have, that's 57 minus 14 times 14, divided by 4 times 62 minus 14 squared. You notice that that gives you 0.061538. You do the same thing for the y-intercept. You plug all the numbers in, and you get 1.34615. This is a bit tedious because you have to plug in all these numbers and do the table, but it's pretty simple. It's just adding and subtracting and dividing and multiplying. All right, let's move on. And finally, we are able to give the equation for the best straight line, which is y equals 0.61538x plus 1.34615. Are we done? Unfortunately, no, we're not, because we haven't addressed significant figures. And the way we do that is by estimating the standard deviation in the y-axis and all the y vertical deviations. The uncertainties in the slope and in the y-intercept are related to the uncertainty in measuring the values of each y point. So that's why we need to estimate the standard deviation in y. And that's the equation for it. You can see it's the square root of the sum of di squared. And I'm showing you what di squared is. We had seen that already. It's just yi minus mxi minus b squared. So that's what you would find. Plug it into there, divided by n minus 2, and take the square root of it. But before we can plug what yi, mxi, and b is, you have to figure out what the standard deviations in your slope is and in your intercept. And those are two separate equations that I'm going to show you right now. These are the individual equations for the standard deviation of the slope and the intercept. And as I wrote here, don't freak out. It's the same things that we've already have the values for all of this. It's the same thing. So just plug all the numbers that you need in, and you notice that the SY, which I just showed you the equation for in the last slide, is here. We plug in all the numbers. Obviously, it's going to be 4 divided by all of that, which ends up being 52. But anyway, these are all numbers that you have in your table. Just plug them in, and then you can find what the standard deviations are for all of this stuff. Let's go on to the next slide. And here you'll see that I've added more stuff to our table. We have the original stuff that's on the left, and then I've added what DI is, which is YI minus MX minus B for all of the points. And then I went ahead and squared what DI is, so I can get all positive numbers. That's the whole point. Once you do this, then you're ready to figure out what the correct number of sig figs for your line is. And here I'm showing it to you. So the standard deviation in y, which was the original equation, was the sum of di squared over n minus 2. So di squared, the sum of it is in the bottom of your table, and then you take 4 minus 2, square root that, and you get 0.19612. So you plug that number in to the standard deviation of the slope and the standard deviation of the intercept, and as well as all the other numbers, and that's how you get 0.054394, and then of course for the intercept you get 0.21415. Like I said, this is a lot of numbers. It's very tedious, but is it hard? Absolutely not. Do you have to memorize these equations? No, you don't. All you really need to know how to do is how to use it, how to figure it out. So finally, at the end, you can combine all the results, and you see that the equation for your line originally was y equals 0.61538x plus 1.34615. That's what we had gotten before we did any of the significant figures. We just figured out that the standard deviation for the slope was 0.61538 plus or minus 0.05439. Remember what the rule was. That first significant digit in your standard deviation, that is as far as your answer can go. So since it's 0.05, your answer, the value, is only going to go to 2 decimal places. So it's 0.62 plus or minus 0.05 for your slope. What about for the y-intercept? Well, it's 1.34615, but the number that you had gotten for your standard deviation was 0.21415. It's that first decimal place. So you can only go up to that first decimal place in your answer. So it's 1.3 plus or minus 0.2. So finally, we get the equation of the line with the uncertainty. It's 0.62 plus or minus 0.05x plus 1.3 plus or minus 0.2. And there you go, guys. That is how you do the method of least squares by hand. Now, I'm sure you can probably appreciate that Excel does it for you just by plugging in numbers. It does this all for you, but it's nice to know that you can do it on your own. Please practice how to do these and how to create those tables, because you're probably going to be asked to do that in your exam. All right, guys, I'll see you later.